In this video we're going to do a few more examples on trigonometric integration by trigonometric substitution. So you'll see here we've got 1 over the square root of 25 minus x squared. It's still worth checking if any other method will work. It's not going to be partial fractions. We can't factor it because of the square root. It's not going to be substitution because u would be 25 minus x squared, so du would be negative 2x. So we're left with trigonometric substitution. You can usually identify it as looking like one of the inverse trig derivatives. Another clue are of course square roots, but usually you're looking for something like a constant minus something squared, or something squared minus a constant, or a constant plus something squared. That's usually what we're looking for. So I think it'll be helpful to start by drawing a triangle. Let me do that just right over here. I like to kind of put that off to the side. So draw my triangle. I'm going to put theta right here. I usually, if possible, like to keep x across from theta, so I'm going to put that here, put 5 here, and then this will be 25 minus x squared. You're trying to create a Pythagorean triangle that models the information you've got. And we've really done a nice job here, I think, because it even has the square root in it. But remember, it's just the square root of the constant, the square root of the variable piece. And again, the reason I picked this x to be across, it just makes life a little bit easier if you have that. So now I like to write down my trig, what I know about trig using the two pieces. I like to avoid using the thing with the square root. So of course I have an opposite and a hypotenuse, so we're talking sine. So the sine of theta is equal to x over 5. And from here I can get a lot of information. I can say that theta then is the inverse sine of x over 5. I can say that x is equal to 5 sine theta. And I can say that dx is equal to 5 cosine theta, like that. Okay? So let's start replacing things and rewriting our integral for a trigonometric substitution. So I've got 1 over square root of 25 minus, instead of x, I'm going to replace that with what x is equal to, so 5 sine theta squared. I'm going to replace the dx with 5 cosine theta, and I should have written a d theta. Let me just go back and write that to be notationally correct. Okay, well, second pass at this, I can say that it's 1 over square root of 25 minus 25 sine squared theta multiplied by 5 cosine theta d theta. You'll notice that I can factor a 25 out, so I can rewrite it as 1 over square root of 25 multiplied by 1 minus sine squared theta 5 cosine that. And I'm going to bring this, first of all, let me start pulling things out. I'm going to bring the 5 out here. This, I can pull out the square root of 25. I can pull that out. Of course, square root of 25, I'm going to write it, but it's 5. But I'm going to pull that out because that's now a constant. So out front, as I rewrite my integral again, I just have 1, because 5 over the square root of 25 is 1. I have 1 over, well, 1 minus sine squared is the same as cosine squared. So I've got the square root of cosine squared, and then I've got a cosine theta d theta. Well, of course, the square root of cosine squared is just cosine. So these two things divide to be 1. So my integral is just d theta. And the integral of d theta is theta plus a constant. And I know what theta is equal to. It's the inverse sine of x over 5. So we put it back to be in terms of x. It's the inverse sine of x over 5 plus c. And that's it. In this example, we've got, again, a square root. You know, it's tempting in this case to think, well, why couldn't I make u equal to x squared plus 16? Then du would be 2x, and I do have an x. But it really only works when what we have is in the numerator. Okay, it doesn't really work with the x in the denominator. So let me create my triangle. Okay, theta goes here. I like to have x across. Because it's being added, you know, because it's x squared plus 16, this piece will represent the hypotenuse, you know, because we add the two sides together to get the hypotenuse. So this will be 4. This will be the square root of x squared plus 16, like that. Okay, so let me start filling things out. I had the opposite and adjacent, so this is going to be a tangent. So I know theta is the inverse tangent of x over 4. I know that x is equal to 4 tangent theta, and I know dx is 4 secant squared theta d theta. Okay, let's go back in and start replacing things. Okay, I'm going to try and put it up here because I think I'm going to need the room. So I'm going to actually put the dx on top this time. So I think we can see the cancellation a little quicker. I'm just going to write the dx like that. Okay, so we're going to have 4 secant squared theta d theta on top. That's our dx. And then down here we're going to have 4 tangent theta, and then the square root of 4 tangent theta squared plus 16. Okay. Well, notice right away the 4's are going to divide out to be 1. Okay. So let me rewrite this maybe a little bit neater. Got secant squared theta d theta over tangent of theta multiplied by, and let's square that, so 16 tangent squared theta plus 16. I'm going to factor a 16 out. Okay. I'm just going to pull that out. Which means I have secant squared theta d theta on top. I still have that tangent theta on the bottom. I have, now the square root of 16 is 4, so I could just write it outside and say it's 4, and then 1, or tangent squared theta plus 1, like that. So let me pull the 4 out. It's in the denominator, so it's going to be 1/4. Tangent squared plus 1 is secant squared. Okay, so this right here is one of our identities. The square root of secant squared is just secant. So I now can rewrite my integral as secant squared d theta on top, tangent theta on the bottom, and secant theta also on the bottom. So of course one of the secants cancels with that secant. Now secant theta divided by tangent theta, well, let's maybe rewrite this with some trig. Secant, of course, is 1 over cosine. Okay. Dividing by tangent is the same as multiplying by cotangent, so we're going to have cosine over sine. So these are gone, so we just end up 1 over sine is cosecant. So it's just the antiderivative of cosecant. Now, this is similar to secant, which we talked about in class. I can post another video with that proof again, but let me just remind you that this is the negative natural log of cosecant theta plus cotangent theta plus c. Okay. So now we need to go back to put this in terms of x's. So negative natural log. Okay. Cosecant, remember, is cosecant of theta is the reciprocal of sine. Sine is opposite over hypotenuse, so cosecant will be hypotenuse divided by opposite. So the cosecant of theta will be hypotenuse divided by opposite, and cotangent, instead of being opposite over adjacent, will be adjacent over opposite. Put a plus c there at the end, and that's it. Sometimes this is the hardest part, getting to this at the end. And let me just remind you real quick how we got this. We needed to replace and get back to x's. Well, cosecant is the reciprocal of sine. So I go back to my triangle and I say, well, sine was x over square root of x squared plus 16. So cosecant would just be the reciprocal. Cotangent is the reciprocal of tangent. Well, tangent would be x over 4. So cotangent is the reciprocal.